former employee here that knows.
Hi, can you hear me? Okay, so any questions before we start? Okay, so the midterm is on Monday. Uh, so yeah, just there have been a lot of changes about how things are going. Were happening. I said it would be on Zoom, but it's for you. The exam would be on my lab as is a my lab assignment. Okay, so you should access the assignment at 9:40, the time that you were in the night, and yeah. So it's going to be slightly harder than the rest of the problems. So please make sure that you practice enough problems. It's open notes. Uh, so so you can use any of the material that like in notes and textbooks. So that's why problems will be slightly harder. So please practice enough problems. Okay. And let's see. So if you have any questions tomorrow, I'll have office hours. So office hours. So my standard office hours are from 2 to 3:30 tomorrow. Uh, but if you can you see the screen? Yeah. Okay. So 2 to 3:30 tomorrow. So please, if you have any questions, please come and ask questions. If you want to solve some problems or anything, so please come and attend the office hours. So the office hours, you can access the office hour link on Zoom. Okay. Zoom homepage, you'll see the, sorry, not Zoom, Canvas homepage. Okay. So So that's some information. So please, if you really have, if you want have any questions, please come and talk to me. So anything else? No, you can. You should like. Okay, so there are. So for instance, so yesterday's problem has something like this, right? So some stuff like this. Yeah. So x is going to 2. So xy is going to say 1, 2. So this limit is essentially, you can separate. I mean, it's the limit is as y goes to 2 of sine y minus 2 over y minus 2, and limit as x goes to 1 of x squared minus 1 over x squared, x minus 1, sorry, x minus 1. Yeah, so if you know both these limits, you can compute limit of the previous stuff. So and this, for this, yeah, this is from your one variable limits, apply L'Hopital, or you know the limit of sine x over x is 1. So you get 1. Similarly, this is limit of x plus 1, or you can apply L'Hopital, you get 2x over 1, so limit is 2. Okay, so you put them together, so the limit will be actually equal to 2 times 1, which is 2. Is that clear? So when you can apply limits, so whatever you do, you should be able to apply. So computation of limits, if you can just compute by using your one variable techniques, you should be able to do it. Okay, if you can use one variables, any of the techniques in one variables, you should try to do it with those one variable techniques. Okay. Anything else? Yeah, so the last class I messed up something, put some limit, but it was not a big issue. I just made some mistake somewhere. So I'll probably send a note sometime, but it's nothing much. Yeah. Okay. So let me, so we'll have a lot to cover today. So I'll just continue. So what we cover today will also be included in the midterm, but it's not really hard. The content of today is about something called partial derivatives. So you should practice how to compute these partial derivatives. Okay, so but before that, let's see what we are doing. So we are trying to understand how to compute limits. So let me summarize what you've learned. So how do you compute limits? The first thing is to substitute and compute. If I substitute, for instance, a limit like this, x squared minus y over ln x plus y. If I substitute, you get 0 over ln 6, so that's 0. Okay, so whenever you can, if functions are nice, you can always substitute. So that's one thing. So something like this, you can substitute and you get an answer. Sometimes you might have to simplify and then substitute. For instance, if you have an expression limit of x squared minus y squared over x minus y, if I substitute, I get 0 over 0. But if I simplify the expression, I'll get x plus y here. So, and then if you substitute, you'll get the answer. Okay, so sometimes you might have to just do some, this is all something like one variable techniques. There's no difference between multivariables and this one variable. You just simplify your limit till you can compute the limit. Okay, and again, you might have to, sometimes you can use things like L'Hopital. So if you have a limit like sine xy minus 2 over xy minus 2, xy is going to 2, 1. So then if you substitute, you get sine 0 over 0 again. So what you do is, if you think of xy minus 2 as s, so the limit is nothing but s sine s over s. And if you apply L'Hopital, you get 1. Okay, so that's one more technique. Then there are techniques like squeeze theorem. So if you want to compute the limit of x sine 1 over x squared plus y squared, you know that, so what squeeze theorem is about, bounding the expressions that you have using some numbers. For instance, if I bound if I say that the sign is between -1 and 1, then my function will be between -x and x. So if I take the limit, I'll get on both sides, take the limit of this expression, you get 0 is less than, our limit is less than or equal to 0. So our limit equals 0. Okay, so there are times where I don't know what, so there is some complicated expression. So I just bound it with some simpler values like -1 and 1 here, and that will help me to compute the limits by taking limits on both sides. So just bound the function by some simpler things, then you can compute the limits. So this is also very much like the one variable technique. So that's not really different. And then one more technique that you might want to use to compute limits is this squeeze polar coordinates. So if I substitute, so here the limit xy going to 0, 0, x squared y over x squared plus y squared. If I substitute x equal to r cosine theta, y equals r sine theta, the polar coordinates, the limit will be limit r goes to 0 of some expression like this. If I simplify, you get limit r goes to 0 of something. Okay, so this limit as r goes to 0 of r times something. That something is always between -1 and 1, right? The something, this cosine theta squared, sine theta squared is always between -1 and 1. So that's why the product of r and cosine squared theta, sine squared theta is between -r and r. So if you take the limit, you'll get both the limits as 0. So the main limit will also be 0. So this is limit as r goes to 0 is 0. This is 0. So the main limit will also be 0. Okay, this is how you apply polar coordinates. Sometimes you might want to just write r cosine theta, r sine theta, and then see if you can compute the limit. So this is one more technique. Again, so there are different techniques. So you should check which might, so if you practice enough problems, you'll know which might work. Okay, that's if the limits exist. Oh, so the Maclaurin, so in the recitation you have done something, and that's here he's explicitly asking you to use squeeze theorem, right? He's telling you to apply squeeze theorem. Like he's giving you the bounds, and using that bounds you're supposed to compute a limit. So you'll know how, like once he tells you what are the bounds, you're expected to use squeeze theorem. And yeah, so I can't say what is expected on the exam, but yeah, so you should practice enough number of problems. Okay, that's yeah, it's a part of the syllabus. So okay, but it's in general you're not expected to know that bounds, the bounds. So that bound is much harder. Like here, the sine theta is less than or equal to 1 is something that you know, but like that tan inverse of x bounds, you don't know how they look. So you're not expected to know those bounds. Okay. Okay, so these are all for showing how how limits exist. So there are different techniques. So please practice them. Some one variable techniques, some techniques with polar coordinates, and some squeeze theorem that's also related to one variable stuff. I mean, it's essentially generalization of one variable stuff. Okay, that's if the limits exist. If you want to actually, if the limits exist and you're trying to calculate them. But if the limits don't exist, so how do you prove that the limits don't exist? So the idea is that we try to show that the limits are different along two different paths. Okay, this is called the two-path test. So we show that the limits are different along two paths. So for instance, consider this limit x squared over x squared to the y to the 4. If you take y equals 0, that means along x-axis, this is x-axis. If you're moving along x-axis, if this is the path, if you're moving along x-axis, that means y equals 0, you'll see the limit is 1 if I substitute. Similarly, x equals 0, that means you're moving along y-axis to 0, 0. Then you see that the limit is 0 over y to the 4, which is 0. So that's why the limit doesn't exist, okay? Is that clear? You show that two different directions, the limits are different, then the limits will be different. I mean, the limit won't exist. Okay, so that here I used the path along x-axis and the path along y-axis. Yeah, if you have two different numbers in two different paths, then the limit won't exist. Because for the limit to exist means that every limit should be the same, right? If every limit is the same, it exists. If it's not, then the limit doesn't exist. So if there are two different numbers, it means that it doesn't exist. Okay. Next, let's take something like this. So a different expression, x squared y, x to the 4 plus 3y to the 4. Now if I take the limit along x-axis, you can compute, it will turn out to be 0. If I take limit along y-axis, that will also turn out to be 0. But that still doesn't, so you have along two axes, the limit equals 0. But doesn't mean that the limit will be 0. Okay? So you have to check for more paths. So for instance, if I substitute the path y equals mx in this equation, you'll see that if I simplify, the limit will be m squared over 1 plus 3m to the 4. So these two are different. So you get a 0 along some axis, and you get some number like m squared over 1 plus 3m to the 4. So these two are different, so the limit doesn't exist. Okay, so it's not, maybe it's not, sometimes you might have to just check the axes. Sometimes you might have to check axes, you might have to check lines like y equals mx. Okay, if I substitute y equals mx, then you'll see different numbers. And sometimes even y equals mx is not sufficient. So for instance, if I have a function like this, if I substitute y equals mx, you will get 0 always. Okay, so along all these axes, you're getting the limit equals 0. Okay, however you go to the, if you go in straight lines, if you go along lines, the limit will always be equal to 0. So, but doesn't mean that the limit is equal to 0. There are no tricks. It's just you look at the expression and kind of see if, yeah, so there are no real tricks. For instance, even these might not work. So, I mean, once you, I mean, these are just computing these limits, right? So just see which limits are working out and not working out. So it's a matter of practice, right? So you want to have two different limits. Can you, so idea is to see if you can make the expression have two different limits. Okay, so try to find ways to make sure that you have two different limits. Okay, so there's no fixed method. For instance, even these methods I've written might not work if you have a complicated function. Yeah, so just try more and more paths and see if you can get better limits. You can get different limits, okay? For instance, so in this case, if I substitute y equals mx, you're getting a limit of 0. But if I substitute y equals x cube, a different function, you're moving along a different curve. So if this is the curve you move along instead of the lines, and if you substitute y equals x cube, the limit is a half. So that means you have different limits again along two different paths. Along a line, it's 0. Along this curve, it is half. So the limit doesn't exist. Okay. No, the question won't tell you the limit doesn't exist. You have to figure out if it exists. You have to compute. If it doesn't exist, you have to show two different paths. Okay. Either you show it exists and you compute. I mean, either you compute and show it is existing, or you just show two different paths so that the limits are different. Okay, so it's slightly tricky. It needs practice. No, even for the one before, I get 0 on one, if I for some value for some axis and a different value for a different axis, right? If the limits are the same, how do you know when to stop? Yeah, there is no fixed algorithm for it. It requires practice to find. Okay, so for instance, if I give you a random function, like completely random function, it's not easy to know so when to stop. But typically, you can imagine that in your examples, so like something like y equals mx or y equals some x squared or x cube or something like this will work. Okay, but in principle, in general, it could be much more complicated. So there is no fixed algorithm to say, oh, do this and you stop. Okay, questions? So please practice problems on this. So if you have, so if it exists, it's basically one variable techniques, kind of. So some things that you can simplify and compute. If it doesn't exist, you have to show two paths along which it doesn't exist. So that's about limits. Okay, so now let's move on to derivatives. So we started with limits. So if we're trying to do calculus on the functions, you have functions f of xy or f of xyz. So now you want to do calculus on this. So what is the next concept? So we studied limits and continuity. So continuity is related to limits. So now can you tell me what is the next concept that you would study? You want to study derivatives, right? So we follow everything that we did in calculus course. So we studied limits and then we went to derivatives. Similarly, we want to take derivatives in this context. So, okay. So if you have a function of f of xy and you want to take some kind of derivative. So what does derivative mean? Derivative gives you some way to measure how the function changes, right? You want to understand how the function is changing. So there is some function. So, but the function now is like a surface instead of a curve, right? Because for every xy, there is some point and you will have like a surface defining the function, and you want to understand how the surface is changing, right? In the case of a curve, the derivative will tell you how the function is changing by taking the slope or some aspects of the slope. But now on the surface, I can move in many directions, right? It's not so from every point, I can move in many directions and the function changes in every direction. So how do I quantify how the function is changing when you move from a point? So that's the question. So any ideas? How do you measure how the function is changing if you move from a point? Right, you want to define something like a derivative. Okay, so let me tell you, there are two different ideas. So there's something called partial derivatives. Yeah, so this is called partial derivatives. So what it means is that you think of one of the variable as constant. So for instance, if you want to partial derivative with respect to x, means that is written like this. Instead of df over dx, you write it as dou f over dou x, a slightly curvy d. So dou f over dou x. It just means that you're thinking of y as a constant. Okay, you fix y. So all this means is that partial derivative of f with respect to x means that you fix y. So fix y. So y is like a constant, and then compute the derivative. That's what it means. So geometrically, what does it mean? You are moving. So if you have on the plane, you are at a point, you can move in any direction, but you're only moving along x-axis. So you take the derivative as you move along x-axis. So that is the partial derivative with respect to x. Similarly, if I fix x and take the derivative, okay, if I fix x and I'm taking the derivative with respect to y. So this is different ways to write derivatives. This is going to definitions, the limit definition of the derivative. But in any case, if I fix x and take the derivative with respect to y, it's called the partial derivative with respect to y. It's written, again, there are different ways to write it. You can write it as dou f over dou y, or you can write it as fy. So these are different notations to write the derivative of partial derivatives of the function. So are these ideas clear? So fix one of the variable and take the derivative. That is called a partial derivative. Questions on this? It's really important. Okay, so let's take an example. Before that, again, so let's see. let's take something like this. So if you have a function like that, which you can see, so what does it mean to take a partial derivative? So at this point, you can move along different directions, but if you move along x-axis, you get this function. The derivative of this at this of this curve, the slope of this curve is called the partial derivative with respect to x. But if I move along along y-axis, means I'm moving along this axis, like this curve. The slope of this curve is called the partial derivative with respect to y. Okay, that is geometrically what you mean by partial derivative. You fix y, that means you're moving along this green curve, and you take the derivative. So you take the slope. Similarly, you fix x, that means you're moving along the red curve, and you take the derivative, that means you take the slope, that is the partial derivative with respect to y. Okay. Okay, now let's compute some derivatives. It's completely similar. So to compute the partial derivatives, as I said, fix one of the variable and then compute. So can you tell me what is dou f over dou x? When you compute dou f over dou x, you imagine that y is a constant. Now can you tell me what you get if I take the derivative of this expression imagining y is a constant? Okay, so let's see. This gives you 2x if I take the derivative of x squared. And if I take derivative of 3xy, I get 3y because derivative of x is 1. And now y is a constant, so the derivative of y minus 1 is 0. So this is 0. This is 2x plus 3y. Is that clear? So just imagine that y is a constant. When you do the derivative with respect to x, the partial derivative with x, it's y is like a constant number. Okay, it's not a constant, but you imagine that it's a constant. Okay, then what is dou f over dou y? Okay, so when you take the derivative with respect to y, derivative of x squared is 0, derivative of 3xy is 3x, derivative of y is 1. So this is 3x plus 1. Okay, so, and you can substitute the value 4 and 5, but the main thing is this. So how to compute the partial derivatives. Okay, so let's do one more example. So the derivative, so let's compute. Can you guys tell me what is the partial derivative with respect to x of this function? F is y sine xy. Partial derivative with respect to x of this function. Okay, y is a constant. I'm taking partial derivative with respect to x, so y is a constant. Okay, so it's y times, when I take the derivative of cosine xy, you get sine xy, you get y times cosine xy. So this is y squared cosine xy. Okay. What about partial derivative with respect to y? What is the partial derivative with respect to y? Right, it's, so there are two functions, the product of two functions, you have to apply product rule to get the derivative. So it's y times derivative of sine xy over dou y plus derivative of y times sine xy. Okay, you have to apply product rule. Y squared, so this y from the expression, and when you take the derivative of sine xy, you get, this is the derivative of sine xy. Right? When you take the derivative of sine xy, you get y comes out, right, by chain rule. Okay, now let's see, what is this? This is y times the derivative of sine xy is again y times cosine xy, sorry, x times x times cosine xy, and the derivative of y is 1, so this is sine xy. Okay, so that's the derivative of the function xy cosine xy plus sine xy. Okay, so is that clear? So it's quite simple. So you just practice problems. Imagine that when you do derivative with x, y is a constant. When you do it with y, x is a constant. Okay. So please practice problems like this. Okay, so let's compute one more stuff. So apparently you have an equation. So of this kind, I want to compute dou z over dou x. So what do? I don't have the function z, but you have an equation like this. What do? I want to compute dou z over dou x from this. There's some equation. With x, y, and z. Okay, so so you have an equation, you want to compute dou z over dou x, so just take derivatives. But what derivative do you take? You take dou a over dou x. If I do that to this expression, just apply this derivative dou by dou x, you get on the left side, you get dou by dou x of yz minus ln z. On the right side, dou by dou x of x plus y. So can you tell me what is dou by dou x of x plus y? If I take partial derivative of x plus y, yeah, so y is like a constant, so the derivative of x plus y would be just 1. Okay, that's good. But what is the derivative of yz minus ln z? Can you tell me what is the derivative of yz minus ln z? No. So z is a function of xy. Z is a function of xy. Z is not a constant. Okay, so let's see. So what will that give you? Derivative of yz. Yeah, so z is a function of x and y is a constant, but z is a function. So although even if you put y as a constant, that doesn't mean that z is a constant. Is that clear? If z is a function of x and y, if you fix y as a constant, doesn't mean that z is a constant. Z will still be some function of x. Is that clear? Okay, so now let's take the derivative. So y is a constant, it comes out. And so the derivative is dou z over dou x minus derivative of ln z. Can you tell me what is the derivative of ln z? What is the derivative of ln z? Okay, it is 1 over z if I take the derivative with respect to z, right? So that's why you have to multiply dou z over dou x. It's a chain rule. Is that clear? If the derivative with respect to z is 1 over z, but the derivative of z, we should multiply it with the derivative of z. Is that clear? So you have to apply the chain rule. You can't just derivative of ln z with respect to x would be derivative of ln z with respect to z times. Oh, so this is the whole thing is implicit differentiation. Yes. But instead of taking derivative with x, I'm just taking derivative with respect to, yeah, instead of normal derivatives, I'm taking partial derivatives. Yeah. Okay, and this is 1. So that's it. So from this, you can compute what is the partial derivative of x, z. So if I simplify, so dou z over dou x would be just 1 over y minus 1 over z. Just if I bring out all y, this is, yeah, just take dou z over dou x common. So you'll get dou z over dou x is 1 over y minus 1 over z. Oh, yeah. So in this case, It's fine. So you can imagine. So these are three variables which are related to each other, but he's asking you to compute, right? So this equation is telling you that x, y, z are related to each other. That means that one of the variable will be depending on the rest of the variables. So yeah, for instance, someone can ask you to compute something like dou x over dou z, or dou x over dou y over dou z. That's also fine. Okay, it depends on what question they ask. Here he is asking you, think of z as a function and compute the derivative with respect to x. Is that clear? Okay. Okay, now let's compute more. So again, so this is just, all of them is practice of computing the partial derivatives. Okay, now let's compute the partial derivatives with respect to x and y of this function. Can you tell me what the partial derivative with x is? fx, you want to take the derivative of this function with respect to x. So what do I do? So when you take this derivative, you think of y as a constant, and I want to compute the derivative of this function. So what do I do? No. Yeah, quotient rule. It's 1 over something, right? This is y is a constant, this is a constant, but the function is like 1 over something. So you have to apply quotient rule, okay? So what do I get if I apply quotient rule? So you get 2y minus 1 over y plus cosine x whole squared times derivative of cosine x, which is minus sine x. Okay, this is what you get if you apply the quotient rule. And what about fy? Again, the same thing, just take the derivative. So y plus cosine x whole squared. And derivative of 2y is just 2 times y plus cosine x minus 2y times derivative of y plus cosine x is just 1. So this is just cosine x over y plus cosine x whole square. Okay, the same thing. Even this, I didn't write the complete quotient rule in the first part. I directly gave you the answer. This is the quotient rule. Okay. Oh, y plus cosine x squared. Oh, wait, so let me check. Y plus cosine x minus 2y. So which one, for the first one or the second one? So let's see. So in the denominator, you get y plus cosine x squared. That's fine. In the numerator, you get 0 minus 2y sine x, right? That's fine.
Wait, but for the denominator, it's y plus cosine x. So isn't y a constant? So the derivative of y is 1, or I mean 0. And then the cosine x is negative sine x.
Yes. So okay, if you want me to write it, I did it directly without. Okay, so you get a 0 minus something. So let me, if you want it clearly. Yeah, when there's a 0, I typically don't show the 0. So the derivative of y with respect to x, right? So the denominator is squared times the numerator derivative, derivative of 2y, which is 0, minus 2y times the derivative of cosine x is minus sine x. So that's what you get if you want me to write it properly. So that's what I've written previously as well, but I didn't show the 0. Okay, questions? Just again, just when you're doing this, x is a constant for y derivative and y is the derivative, y is constant for x derivative. Okay. Okay, let's do it for more variables. So it's similar for more variables. So when you do the partial derivative with respect to x, you keep everything else constant. Y and z is constant. Can you tell me what partial derivative with respect to x is? So to compute fx, y and z would be constant. So what would be just the derivative with respect to x? Right? So this would be just 2x plus 0 plus 0. Okay, good. What will be the derivative with respect to y? No, 0 plus z squared plus 0. Okay. What is with respect to z? You get 0 if you take derivative with respect to z. And if you take derivative with respect to z, this is 2yz and this is 3z squared. Okay. So that's the partial derivative with respect to z. So is that clear? So when you, again, even if you have more variables and you take partial derivatives, you think of the main variable as the variable, everything else as a constant. Questions on this? Okay. So you should practice more and more problems. You need to know how to take derivatives. It's basic calculus. The only idea is that you're making one of the variables as constant. Okay. So now, so you can just, once you have derivatives, you can compute higher derivatives. Like in just one variable, you would compute first derivative, second derivative, and so on. But now we're talking about derivative with x, derivative with y, and so on. So the higher derivatives are like this. You can compute the derivative with x and then compute the derivative with x. Such a derivative is called fxx. You take different derivative with x and then x. That's called fxx, or it's written also like this: dou square f over dou x squared. Okay. So these are different notations to take the derivative with x and then take the derivative with x again. But if you take the derivative with y and take the derivative with y again, this is the notation. If you take the derivative with y and take the derivative with x, it's called fyx. First you take y derivative and then take the x derivative, that's called fyx, and it's written like this. So you can in general write any number of derivatives. You can take x derivative, x derivative, x derivative is fxxx. If you write x, y, x, first x derivative, next y derivative, and x derivative is fxyx. Next, if you have more variables, you can take x, x, y, x, z. So is this notation clear? So fxx means you take the derivative. This is order of the derivatives. You take x derivative, then x derivative. Yy means that y derivative and then y derivative. Fyx means y derivative and x derivative. Yes, so we can see that fyx will be equal to fxy, but I'll tell you, yeah, that's it. We'll see it, but there's no difference between fxy and fyx. But right now, I'll talk about it in some time. Okay, so examples. Let's compute fxx or dou squared f over dou xx. Can you tell me what fxx is in this case? First, what is fx? To compute fxx, you need to know what fx is. Can you tell me fx, what is fy, and then we'll compute fxx and fxy. If you take the derivative with x, it's cosine y plus y exponential x. With y, which is minus x sine y plus e to the x, right? Okay, now can you tell me what fx is? Right, I have to take the derivative of this, which is y e to the x, right? So if I take the derivative of f, you get fx, and if you take the derivative of fx again, you get fxx, which is y e to the x. What about fxy? I want to take the y derivative of this. What is fxy? Fx is given to be cosine y plus y e to the x. So you take the y derivative, so which is minus sine y plus e to the x. Okay, good. What about fyy or fyx? Okay, now I have to take the derivative of this expression with respect to x. If I do that, I'll get minus sine y, derivative of x is 1, and plus derivative of e to the x is e to the x. Finally, what is fyy? So this is what you get here. If I want to take the y derivative of this again. So minus x cosine y, right? Derivative of sine is cosine, and derivative of e to the x is 0. So that's minus x cosine y. Okay, so is this clear? So you just keep on differentiating. And which derivative should be taken is given by that symbols. fxx means that you take x derivative and x derivative. Xy means x derivative and y derivative. Yx means y derivative and x derivative. Yy means that this is you take y derivative and y derivative. But you notice something important here. Okay, this is slightly, you use this in a lot of contexts. fxy is something that you computed, like you took the derivative with x and derivative with y. And fyx is something that you computed, and both the things turn out to be the same. Can you guys see this? So fxy turn out to be the same thing as fyx. Okay, this is a very important identity. You can take the derivative with x and y, or y with x is the same thing. So you can differentiate in any order, but you have to take those many derivatives. Okay. Is that clear? So the order is not important, but you have to take those many derivatives. So one x derivative and one y derivative is important. Any questions on this? What is partial derivative? How to take the partial derivatives, higher derivatives? Right? Okay. So yeah, so for instance, if I want to take fxy, xxy, it's the same thing as fxyx, it's the same thing as fyxx. All these things are the same. I have to take two x derivatives and one y derivative, that's it. Okay, this is really important, we'll see, because sometimes computing one of them might be easier and computing the other might be hard. Which of the derivatives matches sorry, can you say it properly? I didn't understand what you mean by which of the derivatives matches fxy, fyx. You can speak if you want. Oh, okay, okay. So this is the first, this means you take the x derivative first and this is the y derivative first. So next, so you should think of it in the order, right? So you apply the, so this is nothing but dou over dou y over dou over dou x. So this is f, so it's kind of reverse, right? Yx, if I write dou square dou y over dou x, it means it's fxy. You take the derivative with x first and then derivative with y next. Okay, so it's slightly reversed. Is that clear? So do y of do x of f is nothing but f x y. Right? Is that clear? You take the derivative of x first, f with x first, and then you differentiate with y. So it's kind of reversed. In some sense, it's reversed. Okay. Okay. So as we have seen, so the important result. So this is an important. So we have seen it in the example. Fxy equals fyx. So the order of the differentiation doesn't matter. Okay, that's what we have seen. You can differentiate in any order. So fxy is fyx. fxyz is the same thing as fxzy or anything. So you can shift the order in any way you want. Okay. So that's something important about this mixed derivatives. Okay. And that typically happens if f is a nice function. Okay. So you can't do it for all the functions. You can have some crazy functions where it's not true. But if you have nice functions, it's always true. Okay. So let's see. Can you guys tell me what f, let's compute this, is a w here. Can you compute wyx? This is wyx. You're differentiating with y and then with x. Can you tell me what it is? He's asking you to compute wyx. What is wyx? Okay, first, what is wy? Can you tell me what wy is? Take the derivative with respect to y of this, which is x plus, what is the derivative of this? This is nothing but you to apply chain rule. Sorry, quotient rule, y plus 1 whole squared. Derivative of this, y squared plus 1 minus exponential y. Derivative of y squared is 2y. Okay, so that's wy. What is wyx? Can you tell me what wyx is? Yeah, so this is 1 here, and then this whole thing is a function of y, so that's 0. So this is just 1. Okay, so wyx is just 1, right? Good, but let's see. So can you tell me what wxy is? So what is wx? Wx is nothing but y. So therefore wxy, because when you take derivative of x, this whole thing gets cancelled. You don't need to worry about the second term. So you get y, and wxy, if you take the derivative with y, is just 1. Okay, so both ways you get 1. But can you see that the second method is easier? Because I don't need to compute this expression. So if I do it this way, it's easy to see the answer is 1. Yeah, so you can use either one. Okay, so if you use, right, because they're the same answer. If I use this method, so in this case, so you should try to use something that simplifies your answers. So if I use this, you'll see that the answer is much easier instead of this. Right? I don't need to do much computation. But here I have to do this chain rule and so on. Sorry, not chain rule, quotient rule. So is that clear? Right? So you can compute it any way, but you should decide which way is simpler. For wyx, yeah, so you think, no, when you differentiate, for wy, x is a constant. But when you, after wy, when you differentiate with x, y is a constant. Is that clear? So wy is this function. Now when you're differentiating with x, right? the main derivative is with respect to x. Wy is the function that you're differentiating, and you're differentiating with x. That means y is constant. Is that clear? So that's why it's 1 here. Or if you wx is y and you're differentiating with y, so y will get you 1. Okay, so good. So let's do more. Can you tell me what this answer is? Fy xyz of this expression. Okay, so which one do you want to do first? Can you, so it's better to do z, right? Because there are two z derivatives, and z, the function is very simple in z. Okay, did you get why you would want to do z? The function looks very simple in terms of z. That's why we do z. Is that clear? So so fz would be just 0 minus 2xy squared plus 0. Okay, so fz is quite simple. Okay, now what else do you want to do? Now you'd want to do z, right? X, right? Yeah, because x, it's simple in x. In terms of x, it's quite simple. So fzx is minus 2y squared. Okay, next, what do you want to do? Next you are left with two y derivatives, so you have to do them. So fzxy would be minus 4y, and you do one more. fzxyy is minus 4. Okay, so is that clear? So you should always choose the simplest path way to do it. For instance, if I start off with y derivative, I will have to, or x derivative, you'll get more terms. It's unnecessarily complicated. But if starting with z derivative simplified our process. So is the idea clear? So we can do it in any order. So you have to choose the simplest order that you can imagine. Okay, so let's move on. Okay, so there's something about the relation between partial derivatives and continuity, right? So do you guys know that if a function is differentiable, if it's a one variable function, if f of x is differentiable, then it means that it's continuous. You know this, right? It's not true other way around, but if it is differentiable, it has to be continuous. Can you guys see this? You might have known this in one variable stuff. If it is differentiable, it is continuous. But if it is continuous, it might not be differentiable because it might have some V-shape kind of things. Even if it's continuous, it doesn't mean that it is differentiable. But if it is differentiable, it definitely will be continuous for one variable functions. But what happens in the case of partial derivatives? If you know that the partial derivatives exist, can you say that the function is continuous? What do you think? Okay, so partial derivatives is telling you that the function is nice along x-axis, along y-axis, but it's asking you whether it will be continuous. So you should not expect something like that. If the derivatives are also differentiable, then you would expect continuity, but right now we don't know what's happening. But if you all you know is that the derivatives exist, you can't really say anything about continuity. So the answer is no. Okay. So in one variable, if it's differentiable, you get continuity, but in more variables, partial derivatives won't imply continuity. Okay. Just having partial derivatives won't give you that the function is continuous. Okay, so you can take some example in this case. For instance, there's a function which is 0 when xy is not equal to 0, which is 1 if xy equals 0. Can you tell me what is it? What is the limit as xy is going to 0, 0 along x equals y of f of x, y? X equals y. Can you tell me what is the limit now? Right, the function is 0 if xy is not 0. So x equals y and x not equal to 0, the function is 0. So the limit will be 0. Okay, but this is not equal to f of 0, 0. F of 0, 0 is 1. Okay, so there's this function which is not continuous because the limits along x equals y is 0, but the function value is 1. So that means the function is not continuous. Okay, so that tells you that the function is not continuous. Okay, the limit is 0, so that means the function is not continuous. But can you tell me what are the partial derivatives of this function? Can you tell me partial derivatives of this function? Fxy dou by dou x. That means y is 0, right? I want it at 0, 0. So I can plug in y equals 0. So what would be the function? What will be the derivative? So y equals 0, that means my function is just 1. This will be my function. So that means the derivative is derivative of 1, which is 0. Similarly, when x equals 0, the partial derivative with respect to y, which is also 0. So that means the partial derivatives are both 0, they exist, but you see that the function is not continuous. Okay, so is that clear? So although the function is nice along x-axis and y-axis, so it's nice along x-axis, nice along y-axis, but you see that if you move along some other axis, there is some issue. X equals y. Okay, so that's why just having partial derivatives doesn't mean that the function is nice. So that is something that you should know. Okay, so partial derivatives just tell you the information about how the function is along axes. Along axes, if you just restrict, if you're moving along axes, the function, what is the derivative is what is the information that's contained in partial derivative, but that doesn't tell you about how the whole function looks around that point. You might, if you look at the points which are not along the axes, the function might look different and weird. Okay, so that's what this example says. Along x equals y, the limit is different from the value at 0, 0. That's why it's not continuous, but it has partial derivatives. Okay, so that's why we would need a different idea of differentiability, not just partial derivatives. This is called the idea of differentiability. Okay, this is, instead of calling partial derivatives, we want something called differentiability or derivative. Okay, so let's see what it means. So do you guys remember what does it mean for the derivative? So do you guys remember an expression like this in calculus? Delta y is f prime x0 delta x. In one variable calculus, you might have seen that this is the linear approximation of the function. F of x is nothing but f of x0 plus f prime of x0 plus times delta x, right? Approximately. So the linear approximation of f. So do you guys remember that? So you can talk of a function is differentiable if you have a linear approximation like this. Okay, this is the way to talk about differentiability in one variable. You can define it as the limit of that ratio, or you can say that a function is approximately equal to the linear function. That's what you mean by a derivative. So that means geometrically, if you have some picture like this, a function having derivative means that the function here looks like the tangent line. So the function close to this point will look like the tangent line at that point. That's what you mean by differentiability. And if you write down what the equation of the tangent, it looks like this. So that's why f is approximately equal to the equation of the tangent. So is that clear for you guys? This is something that you should have seen in calculus. A function looks approximately like the tangent line. So that's for one variable. Okay. Now we can do a similar thing in more variables. The function, now the surface is not a curve. So the surface is like you have a surface, right? The function is a surface, if you visualize. So the idea is that you can approximate the surface by a tangent plane instead of a tangent line. Okay, that's the idea. So if you draw the surface, you can imagine that near any point, the surface, so for instance, on the surface of the earth, right? The earth is like a curved surface, it is going, right? It's a spherical object, but you see that if at any point on the earth, you kind of think that this space is just like a plane. So even if it's a complicated surface, you can always imagine that the surface looks locally like around that point looks like a plane. So that is the idea. So geometrically, for higher dimensional functions, so you can imagine that, for instance, two variable functions, a function is approximately equal to the tangent plane. Okay, so what does that mean if I write the equation of that tangent plane? So the tangent plane equation would be this. This is the equation of the tangent plane. So the function will look like f partial derivative x times delta x plus partial derivative y times delta y. Okay, plus some small error. This is the error term. This is not exact. This is because the tangent plane is not exactly equal to the, just like the tangent line would not give you exactly equal to the function. The tangent plane won't give you the exact function. It will give you approximation. So this is like some error. But if you forget about the error, the function is approximately equal to the equation of this tangent plane. Okay. So if you have something like that, such a function is called differentiable. If you have a function which has a tangent plane, which is not weird, if you can draw a tangent plane, then it's called differentiable. So is that clear? So this is different from having x derivative and y derivative. Okay, so partial derivative x and partial derivative y can exist or not exist, but for it to be called differentiable or have a tangent plane approximation, we need an approximation like this. Okay, that's what you mean by. So epsilon part is the approximation. So this means this is like the error. So the error is, this is small. That's what it means. These errors go to 0. Okay, so this is the exact. This is this first part gives you. This gives you the equation of the tangent plane, and this is the error term. So you're saying the function is approximately equal to the tangent plane. Okay, so that's what is called differentiable. So why is that important? So the differentiability is a stronger condition than partial derivatives. For instance, if it is differentiable, then you will have both the partial derivatives. Okay, but if you have partial derivatives, it doesn't mean that the function is differentiable. Okay, but if the partial derivatives that exist and they're continuous, then the function will be differentiable. Okay, these are some things to know. Okay, so just because you have partial derivatives doesn't mean that you have differentiable, but if you have the partial derivatives which are continuous, then the function will be differentiable. Also, partial derivatives, as we have seen an example, are just looking at the information about x and y. They don't know anything about other paths, so that's why you don't have continuity. Partial derivatives don't imply continuity. But the differentiability means that the function looks like a plane. If it looks like a plane, then it means the function will be continuous. It's looking locally, it's looking like a plane. The plane is a continuous function. Yeah, if the partial derivatives exist, it doesn't mean that it is continuous. What do you mean with the opposite? If it is continuous, also we can't say anything about partial derivatives. But if it is differentiable, we can say something about both partial derivatives and continuity. If it is differentiable, it means it is continuous. It also has partial derivatives. Okay, so just think about it. This could be confusing. Partial derivatives only look at x, y directions, so they can't tell you anything about a derivative or continuity. Continuity alone is a weak condition. It can't tell you whether the function is smooth or not, right? Continuity, so it doesn't mean that the function will be smooth. It might have some weird V shapes. But differentiability means that the function is smooth and it looks like a plane. So that means it gives you all the conditions. So is that clear? So differentiability is the strongest condition. It means the function is very smooth. So this implies partial derivatives. It implies continuity. But continuity and partial derivatives are not related. Any of these things are not related. It's only in this direction. If the derivative is differentiable, if it is differentiable, you can say that it has partial derivatives and it has continuity. Okay. Okay, this is it's the same thing that I've talked about. So if you have, but the thing is, if you have partial derivatives and they're continuous, this theorem says that although partial derivatives alone doesn't mean that the function is differentiable, but if the partial derivatives are continuous, if fx and fy are continuous, then then you will have differentiability. Then you'll have some equation like this, which means it's differentiable. Okay. So this whole thing is just saying that if partial derivatives are continuous, if you take the partial derivatives and they're continuous, implies differentiability. Just partial derivatives won't tell you about differentiability, but partial derivatives with continuity will tell you differentiability. Okay, so this is something. Finally, okay, so I've lost a few minutes, so I'll have to do it fast. So chain rule, this is, it's chain rule in one variable. You know how to, if you want to differentiate a function with t, you differentiate with x and differentiate with t, that's how you differentiate the chain rule, right? So if you have a function of omega x and x is a function of t, and if I want to differentiate w with t, I differentiate w with x and then differentiate w with t. That's the chain rule. So what about higher variables? How do I differentiate in more variables? So let's check. It's the same thing, but now instead of actual derivatives, you take the partial derivatives. So instead of actual derivatives, you take the partial derivatives. Okay, so, but the thing is, this is how the chain rule looks. So if you want to understand how a function is changing, you need to know how the function is changing along x and how the function is changing along y and add them together. Okay, that's what you get if you try to do the chain rule. Okay, the derivative of a function with respect to t will depend on how the function is changing along x and how the function is changing along t. So this will be the formula for the chain rule. So if I want to know how the function is changing as I move along this path, I want to add up how much it's changing here and how much it's changing here, and then I'll get the total change. Okay, so that's one chain rule. So let's take an example. Okay, so w equals xy, x equals cosine t, and y equals sine t. So let's try to compute. I want to compute w over wt. Okay, so how do I do this? So this is nothing but you see how W is changing with respect to X and how is X is changing with respect to T, and add up with how W is changing when you change Y and how Y is changing with respect to T. So is the formula clear? This is really important. So if you want to know how W is changing with respect to T, you should do both the things, because W can change with respect to X and W can change with respect to Y. So we have to add both the contributions. Is this clear? So this will give you the change as because of the change in X. This will give you the change because of change in Y. So now let's compute that. What is do W or do X? Is nothing but Y, right? So Y and do X over do T is nothing but minus sine T, because X equals cosine T. Next, do W or do Y is what? X, and derivative of dy over dt is just cosine T. So, but X is what? X is nothing but cosine T minus sine T. Y is nothing but sine T. So this will be just 0. Okay, so that's something that you do. Okay, now let's compute some other partial derivatives. So what is partial derivative with respect to T of this? So if you want to understand derivative with respect to T of this, so can you tell me what this is? W can change if X changes, and X will change this much. W can change if Y changes, and Y will change this much. And W can change if Z changes, and Z will change this much. Okay, so this is a change because of change in X. This is a change because of change in Y. This is a change because of change in Z. So you add up all of them together, you get the total change in W. Okay, so now let's compute. So can you tell me what this is? Do W or do X is nothing but Y, and do X over do T is nothing but minus sine T. Similarly, do W or do Y is nothing but X, and do Y over do T is nothing but cosine T. And finally, do over do Z is nothing but 1, and do T over do T is just 1. So if I compute this, this is again cosine T minus sine T plus sine T cosine T plus 1. So this is just 1. Okay, so this is the main expression. So please try to understand how you get this. If you want to understand how W changes with respect to some parameter, you have to add up all those contributions. How W can change because of a change in Y or change in X or change in Z. And when W, so you have to add up all the contribution to these changes. Oh, Y is sine T. Okay, good, good. Sorry, I was wrong. Okay, Y is sine T. Good, good. Y is sine T. So this is minus sine squared T. This is plus cos squared T plus 1. Okay, good. That's not 0. Good. Okay, is this clear how to compute partial derivatives? The chain rule. You have to apply this kind of it's related to your essential change rule, but you have to add up contributions because of X, Y, and Z. Okay, so you should think of this. You should think of as change just from X. This as a change from Y, and this as a change from Z. You should add them up together to get the total change of how much W is changing. Okay. So again, and similarly, if I don't want to, if I have more variables, I can take derivative with respect to more variables. Instead of taking derivative with respect to T, I can also derivative with respect to R and derivative with respect to S. Okay, so let's do that. Is that clear? So it's completely similar to partial derivative. Instead of just t, if it is depending on two parameters, you just take the derivative with respect to two parameters. Okay, so let's solve this example. So I want to compute dou derivative with respect to r of this function. So what do I do? So the same thing as you compute the derivative with respect to x, and you see how much x is changing with respect to r. Again, derivative with respect to z, and how much y, and how much y is changing with respect to r. Is this formula clear? The partial derivative with respect to r, you want to know how much it is. You see how much is the change coming due to change in x, how much is the change coming due to the change in y. Okay, so can you tell me what this is?
Today is life.
Give me a second. So I'm getting some. Sorry, can you hear some voices? Let me change. Okay, anyway, I'll just finish this. So dou y over dou x is nothing but 2x. Dou x over dou r is just nothing but 1. Dou over dou y is nothing but 2y. Dou y over dou r is nothing but 1. So it's 2x plus 2y. So that is if I am trying to calculate the derivative with respect to r. But I can also try to calculate derivative with respect to s. Then it's see how much it's changing with respect to s. Okay, so how much w is changing with respect to x, and how much x is changing with respect to s, how much w is changing with respect to y, and how much y is changing with respect to x. So now dou by dou x is nothing but again it's 2x. The partial derivative with respect to y, x is minus 1, of x with respect to x is minus 1. Partial derivative of w with respect to y is 2y, and dou y over dou s is 1. So this is 2x minus y. Okay, so that's how you do the partial derivatives. Okay, so is that clear? So it's essentially, if you want to take a derivative of something with some parameter, like anything, so any a, you compute the derivative of this with respect to that parameter times how x is changing with respect to that parameter, plus derivative of y and how y is changing with respect to this parameter. So this you should think of as what is the change as you change x, what is the change due to y. Okay, if you change a, x changes. If I change x, then omega changes. If I change a, some y changes, but if I change y, then also omega changes. If you add them together, you get the total change. Okay, so that's the idea. So this is how you compute. Okay, so please make sure this is something slightly different from what you have seen before. So adding up this contribution, but it's just something that you need to practice. Okay, so that's it for today. I'll see you on Monday. But if you have any questions about anything, so please come and talk to me tomorrow in the office hours. Okay. So I'm done with the lecture. So any questions? Okay, so Good. So let me